everybody, and welcome to our next topic. So, today we're going to be taking a look at derivative rules. So, last time we looked at the long process. How can I find the equation for a derivative or the value of the derivative using the limit process? But now we're going to take a look at some shortcuts. So, in mathematics, a rule is something that's always true. So, no matter if we take the longest route possible to get to a result or a shortcut, if we always arrive at the same answer, once we've established that rule, we're allowed to use it in place of the long method. So luckily for us, every function's derivative was found using our limit process by someone in the past. Isaac Newton, Gottfried Leibniz, those two guys did all the legwork for us. And because of that, now there are established shortcut rules for certain types of functions. So there are ways for us to get around having to do that limit process every time. So good news for you guys, you never have to do that limit process again if you've made it this far into the course. So um, so basically today we're going to take a look at different function types and those shortcuts that we can use to evaluate their derivatives. So for the first type, constant rule, this one's super easy. So the derivative of any constant function is zero, always, point blank. There's no discussion about it. And if you really think about what the derivative function does, this should make sense. Again, the idea of f prime of x, it tells you the change in f of x. So if I go to a point on f of x, f prime's value tells me how f is changing at that point. Well, the idea of a constant function, it's in the name. Constant functions mean they don't change. So if I start with f of x equals c, its derivative is automatically always zero. The derivative of every constant is always zero because they don't change. They always maintain their value. So that one's pretty quick and easy. So the next one, we're going to focus on polynomial and power functions. So polynomials are x to positive whole powers, but the rule that we use to take derivatives of polynomials actually applies, and it has been proven to apply for radicals, which remember radicals are actually fractional exponents, and negative exponents. There's only one exception to this, and we'll kind of talk about that along the way here. So the rule here is if n is a real number, then the function f of x equals x to the n power is differentiable. Again, it's a well-behaved function, no sharp turns that naturally occur or anything like that. And the derivative of x to the n. So remember this notation, when you guys see the d dx and then it's outside of brackets, it's really the notation that says take the derivative of this stuff, whatever is inside. So this acts like an action. It's telling us to do some math. So d dx of x to the n, the rule for this is we take the old exponent n, bring it down in front as a new coefficient, and then it is multiplied by x to the n minus 1 power. So how does that look in action? So it's a pretty easy process. For the function f of x is equal to x cubed, then f prime would be 3 is my old power, so that comes down in front as a coefficient. And then the base stays the same. It's always going to be that variable x or t, whatever it is. And then the new power is just 1 less the old guy. So what that means is the way that a cubic function changes, the pattern that we notice in their slopes are actually going to be represented by a quadratic function. And one of the neatest ways that I've ever seen this explored is actually just through patterns. So I'm going to make a list of perfect cubes. So 1 cubed is 1, 2 cubed is 8, 3 cubed is 27, 3 cubed is 64, or sorry, 4 cubed is 64, 5 cubed is 125, and 6 cubed is 216. Well, if I find the first changes in this, so arithmetic changes, to get to 8 from 1, I have to add 7. From 8 to 27 is plus 19, plus 37, plus 81, or excuse me, 61. If I can do basic math, I can do calculus, but I can't subtract. 61, and then this guy is 91. Okay. Well, it doesn't look like there's any pattern in there because these are just, they look like random numbers. They're getting bigger, but that's really all that you can notice. But if I look at the differences between these, this is 12, this is 18, this is, where is it, 24, and then this is 30. Well, starts to look like there's a pattern here. 12 to 18, that's a plus 6. 18 to 24, that's plus 6. 24 to 30, that's plus 6. Well, if we go back through and notice something here, this is a row of constant values. This row actually has a linear pattern because remember, linear patterns are a constant rate of change. These numbers are constantly getting bigger by 6. The row before that, this is actually a quadratic pattern. Quadratic patterns are where the rate of changes increase by a constant rate of change. So to go from 7 to 19, it's 12 plus 12. To go from 19 to the next guy, that rate of change actually increases by 6. To go from 37 to 61, that rate increases by that same amount of 6. So it's a quadratic pattern when the rates of change are increasing at a constant rate. So that is actually mathematically proven now using this power rule. So the derivative of every cubic function is actually going to be some quadratic function. In this case, the derivative of x cubed is actually 3x squared. For the next one, g of x equals the cube root of x. Anytime that you guys start with a radical, I recommend that you rewrite it as a fractional exponent. Otherwise, you're not going to notice that it's a power rule and that we can use this power rule to find the derivative. So remember, when it's a root, to find the power, we just reciprocate that root. So if it's cube root or third root, then it's the 1/3 power. So that's my old n. So now to find my derivative, we're going to bring down the old power 1/3, multiply x by the old power minus 1. So it does get a little tricky here with these fractional powers, because if I start with any radical, this is always going to be a power less than 1. So when I subtract 1 from it, that's always going to leave me with a negative result. So in this case, we would get negative 2/3. So all that means is to write our answer in the final form, we just have to get rid of the negative exponents. Remember, to get rid of a negative exponent, that negative sign is telling you that that factor actually belongs in the denominator of a fraction. So this is actually going to be 1/3x to the 2/3. That is the derivative of the cube root of x. So if I wanted to pick out any point on the graph of cube root of x, and I want to know what is the rate of change of this original function, then I can plug that value of x into this derivative, and it will tell me the rate of change of the original guy. The only exception to that is at x equals 0, because if you notice, this derivative has x in the denominator, and we know that x can't equal 0 here. And if you remember from the last video, x to the 1/3 power, this was an example that I talked about where the graph actually has a vertical tangent, and that is why the derivative is not defined when x equals 0. Then for this third one, technically we could consider this guy a rational function because it's a fraction with x in the denominator, but this can actually be rewritten using negative exponents. So we do want to be on the lookout for that, that if it's possible to rewrite this in the form of x to some power, and again, now it's not just polynomials, so we can explore negative exponents and fractional or decimal exponents as well. We want to rewrite it that way because this is really x to the negative second power, and then that allows us to use the power rule to find the derivative. So if that's y, now when we write the derivative in function notation, we write the prime symbol, but if I start with y, then that derivative would be dy dx. That's the notation that we use. So change in y as x is changing. So then for the power rule, old exponent comes down, -2, x to the new power. So when you start with a negative and you subtract 1, it actually gets more negative or becomes a larger number or negative number. So this will become x to the -3rd. And then we don't like to leave answers with negative exponents. That's why we didn't start with any. So we want to put this back in proper form. So we'll send the negative exponent's base back down to the denominator. Now the -2 coefficient is still just a coefficient, so it sticks around up top. where we're left with negative 2 over x cubed. That will be our final answer there. So now now that we know these shortcuts, we can do a lot of the same stuff that we were doing before the long way, but now it's just going to be a lot faster. So for example, if I wanted to find the slope of a line tangent to the function f of x equals x to the fourth at these different values of x, before with the long way, I would have to either do the one limit definition problem to come up with the equation of f prime of x and then plug those three in, or I'd have to do the limit definition with these three different values each time. But now it's so quick and easy. It'll only take us a few seconds. So using the power rule first, this would become 4x to the third power. And then to find the slope of the tangent lines at these different points, we just plug each value in. So when x is -1, f prime of -1 would be 4 times -1 cubed, or -4. So again, that's the slope of the tangent line when x is -1 on that graph would be -4. And then f prime of 0, that would be 4 times 0 cubed, or 0. And then f prime at +1 would be +4. That's it. So again, it's the same concept, but now we have these shortcut rules that will speed up this process and make it a lot faster. So if I wanted to find the equation of a line tangent to f of x equals x squared when x equals -2, again, for the actual equation of the line, like we saw in the last video, it's in point slope form, and it will always have the form of y minus the y coordinate at the point of tangency equals the value of the derivative, which again, that's the same thing as saying the slope of the tangent line at the point of tangency, minus x, or excuse me, times the quantity x minus that c value, or the x coordinate at the point of tangency. So I've given you the x value, this is my c, so we need to plug that into the function to find the y. So -2 squared gives me +4, so that's my f of c. And then for the derivatives value to find the slope, so we'll do our power rule first. F prime of x is really 2x, and then f prime at -2 would be -4. So that is my slope of the tangent line. So then my equation would be y minus 4 equals -4 times x plus 2 because of the double negative. So x minus -2 would leave me with +2. But that's it. That is the equation of our tangent line. So I can't stress enough how much better this is now that we can use these shortcuts. Before we have to do the whole limit process, and it's very time consuming. But thanks to Newton and Leibniz doing all of the groundwork for us, we know that these rules, every time you do a limit definition of x squared, it will always result in 2x. So because of those extra little property or extra work that they've done with all of these, we have these established rules now. All right, so now let's take a look at another rule. So this is the constant multiple rule, or you may have heard this called the scalar multiple rule. Essentially, what this is saying that when we take a function and multiply it by a number out in front, so we change the coefficient, we're also changing the rate at which that function is growing. And again, the idea of a derivative is it's representing the rate of change for a given function. So if we just think of the functions x squared and 2x squared. So for each of these guys, they're both quadratics, but changing this coefficient to a 2 instead of a 1 is a vertical stretch. You guys should remember that from algebra 1 and algebra 2. So it's a transformation. We're stretching the graph out, which really what that does is it takes the old y values of 0, 1, 4, 9, 16, 25, and so on. Not only does it make all of these y values bigger, but it makes the gaps in between them bigger and makes the graph change faster. How much faster? Well, it's twice as fast. I like to teach quadratics with a counting rule, +1, +3, +5, and so on. Well, this function's y values are 0, 2, 8, 18, 32, and 50, and so on. That counting rule has now doubled, +2, +6, +10, and so on. So that derivative is directly tied to this little counting pattern and the idea of growth rates. So when we multiply an existing function by a new constant in front, all that does is directly impacts or affects the derivative in the same way. So if the derivative of x squared is 2x, well, then the derivative of 2x squared is just the original derivative multiplied by this new scalar. Or in a more practical sense, what this really does is when we take the derivative of a power term with a coefficient existing there, we're really just multiplying the result of the variable portion by that existing coefficient. So let's try a couple of these so you guys can see how it's done. So first off, we have to make sure that it's in the form that we know how to work with right now, which is just the power rule. So again, we need x to the n, or in this case, we're going to have some number multiplied in front by x to the n. So this first guy, 2 over x, we need to rewrite this as 2x to the negative first before we can do anything. And now we can apply the power rule. So if it was just x to the negative first, that derivative would turn into -1 times x to the negative second. But there's still that 2 out in front. So essentially what we're really going to do is just when we bring this exponent down and there's already a coefficient there, we just multiply the two of those together. Because this guy changes based on this pattern, but we stretch the original graph, so it's going to change twice as fast as what it had before. So in this case, our dy dx would be -2x to the negative second, or -2 over x squared. 4t squared over 5. Sometimes the constant multiple out in front can be a little bit trickier to identify. In this case, it's not just 4 that we're multiplying by, it's actually 4/5. So when you write fractions like this and the denominator is just numerical, we can actually pull it out in front. So in this case, there's a constant or a coefficient up top as well. So you just pull the 4/5 out in front, and this becomes 4/5 t squared. Okay, now notice the input variable here is different, but that doesn't change any of these rules. We can use any variables that we want to for input and output, and we'll still be following the same rules. So in this case, if I go to do my power rule, it would be 4/5, f prime of t would be 4/5 times 2 t to the new power, which would be 1. So then when we simplify it, our derivative function would be 8/5 times t. So this is always a little tricky for some people. When you go to multiply fractions times a whole number, remember we just put the whole number over 1, so then we can go straight across. That's how I'm getting 8/5. All right, now this one's a much more complicated one. So we've got a couple things going on. First off, our coefficient is actually a fraction, 1/2. So that's a little tricky to identify right off the bat. But when I pull that apart, if I really do this step by step, I can write this as 1 over 2 times 1 over the cube root of x squared. Well, that is tricky for two reasons. I've got a radical and an exponent. So I'm going to worry about rewriting this first. The cube root of x squared is like x squared raised to the 1/3 power. And remember that when I have a power of a power, we multiply. So this is really x to the 2/3, but because it's in the denominator, I'm really working with x to the negative 2/3 right now. All right, so I've gotten it rewritten in the form that I need, and now I can go ahead and apply the power rule. So dy dx, if I bring down the negative 2/3 in front, it's now 1/2 times negative 2/3. We'll simplify that in a second, times x to the new power. Now, when I start with a fractional exponent and I subtract 1, if you can't do this in your head, remember subtracting 1, we need to change that to a common denominator, which is always going to match the denominator of the existing fraction. So this would be 3/3. So -2 minus 3 would give me -5/3. So then it's just a matter of cleaning stuff up. The 2's here are going to cancel, so we're going to be left with -1/3 as our coefficient. So a -1 up top, and then remember this guy has a negative power, so that factor will go in the denominator. So -1 over 3x to the 5/3. Just get into the habit now of fixing any negative exponents. Never leave a negative exponent in there. Sooner you get into that habit, the better off you'll be moving forward. All right, now the last one, again, same idea. When it's in fraction form, that notice there's no variable down there in the bottom, so this is just a fractional coefficient. I'm going to pull that out, separate it, and so I've got -3/2 times x. So this is really x to the first power. So even with the x to the first power, we can still do the power rule, but what you do need to always understand is this is a linear function. X to the first power is linear, which means its derivative is always going to be a constant because these are the only kind of function that have a constant rate of change. So because of that, that rate of change is just this slope value. So that's one easy thing to do here. So technically, I can write this out as the power rule, the same format as these other guys. But when I subtract one from the old exponent, I'm always going to be left with 0. Remember, anything to the 0 power is 1. So multiplying by 1, both of these are actually just kind of irrelevant. It's not that they're canceling anything out. It's just multiplying by 1 is not going to change the value. So your final answer is still just -3/2. So that you can still always execute the power rule if you want to, just like that. But just realize when you recognize that it's a linear function, that variable will always disappear because of the power rule, and we're always just going to be left with that coefficient in front. This next batch of problems, they're going to operate in a similar way, but just they represent a couple different variations, things that you guys want to be aware of when trying to do these problems. So for the first one, fairly straightforward. We have a fractional coefficient out in front, so I'm going to rewrite that with the 5/2 pulled out in front. But then x cubed is in the denominator, so when I move it up and isolate it, it's really x to the -3rd. Now we can do the power rule, so we would get dy dx. Bringing down the -3 would give me -15/2. And then my new exponent will be x to the -4th. Again, with those negative powers, um, we get smaller, or really it's a bigger negative number when we subtract 1. So x to the -4th really means x to the 4th in the denominator. Again, don't leave negative exponents in your final answer. Now, now, the next one is a little unique because we have a product in the denominator raised to that third power. So remember, when we have a product raised to a power, we have to distribute that exponent to each piece. So when we go to rewrite this guy, we're actually going to end up with 5/2 cubed, or 8, to then the x to the third power. We want to fix that before we try and rewrite. But after that, it really operates the same way as these other ones. So we'll separate the coefficient, 5/8 is a constant multiple, x to the -3rd. And then just like we saw before, we'll bring down the -3 and then subtract 1. So we're going to end up with the -15 up top over 8 instead of 2, but then x to the 4th power in the denominator again, because even though we change the constant multiple, the function itself is x to the -3rd. So its derivative is still going to end up with the same new power. So the only thing we're changing here is the coefficient. You guys can see how that really doesn't impact the x at all. All right, now for the next one, we have x to the -2nd starting in the denominator, which actually means that it belongs in the numerator. So when I rewrite this, we have 7/3 times x to the +2nd power. So when I bring it up, we change the sign no matter what. That's the rule. And now to take the derivative of that, that one's pretty easy to do because now we just bring the 2 down, so we get 14/3 x to the first. You can put the 1, but we don't have to. So we end up with 14/3 x as that final answer. And then the second one, similar idea. Now for this one, instead of distributing the -2 power right off the bat, because it's a negative power, I can actually move that whole thing up top and make it turn into a +2 power. Now when I distribute, it makes it a little bit easier. So I get 7 times 9x to the second, or 63x squared. But again, we haven't done any calculus yet. Now we have to take the derivative of that it's been rewritten. So now we end up with 126x as our final answer. So now we know how to use the power rule. We know how to use the constant multiple rule. So now we have to take a look at, well, what happens if we have more than one term in our function? So that requires the sum and difference rule. So the sum or difference of two differentiable functions, f and g itself, is still differentiable. So if I can take the derivative of the first part and the second part, but I want to combine them, well, it just means we do the derivative twice. So we take however many terms we have, and we're just going to isolate their derivatives. So if we know that the derivative of x squared results in 2x, and the derivative of 5x cubed results in 15x squared, well, if we take x squared and 5x cubed and combine them to make one function, y equals 5x cubed plus x squared, well, then the sum or difference rule is really just saying take the derivative of each individual term on their own. So how this guy changes doesn't impact how this guy changes. We just want to make sure that they're each making their contribution to the derivative. So their result is just the two individual derivatives added or subtracted together. So it's a pretty straightforward rule. It just means we have more work to do. So instead of just doing one power rule, we're going to do it for each term. So for example, if my function is f of x equals x cubed minus 4x plus 5, then the way that this function changes will have three contributions to it. So the cubic term changes based on a quadratic pattern, so we get 3x squared. The linear changes based on a constant pattern. Again, that would be the slope, -4. But then the 5, that constant actually doesn't do anything to the derivative because this guy has no change. It's a constant term, which means it always holds the same value. So what that really means is if you were to look at this function compared to x cubed minus 4x plus 10, both of these guys have the same derivative. They both change based on the function 3x squared minus 4. And we can see that if we go to Desmos, if I type in x cubed, x cubed minus 4x, and I'm going to put plus c. So what that means is if I just change the value of this constant, if you look at it, I'm not changing the shape of the graph. So which values of x have a increasing curve or a positive slope, or where the graph is really steep, the values of x corresponding to those parts of the graph aren't changing. At x equals -2, that graph is really steep, no matter what that c value is. So the steepness of the graph is not changing corresponding to the x values when all I do is change that c value, because if you think about transformations, that's the y-intercept of this function, and changing that, all that does is serve to shift the graph up and down. So that's why the constant term within these functions, the derivative of a constant is 0, which again means that it doesn't make a contribution to the derivative because it's not changing. So that's one really important thing to keep in mind when we're taking these derivatives. Now for the second one, again, there's no set rule on the number of terms or how many different pieces you can have. We take the derivative using the strategies we've already talked about for each one of these guys. So for that fraction in front, I want to rewrite that though first before I take the derivative, just until you guys get used to this and so we don't miss anything. So now taking the derivative, I get -1/2 times 4 leaves me with -2x cubed. 3 times 3 gives me 9, and new power is x squared. And then this linear term turns into a constant of -2. And that is my derivative. All right, now let's talk about our favorite topic, trigonometric functions. So there are some fun little proofs for these. I used to show these years ago in AP calculus, but with not having as much time to dive into stuff, we're really just going to go ahead and talk about these. Now, one thing I do want to point out, we can do this a little bit faster with Desmos, is one thing to keep in mind is what that derivative function is telling us. Again, it's representing the slope of the curve of our original function at different values of x. So where this sine function is increasing, any tangent line would have a positive slope. The steeper the curve, the steeper the tangent line would be, which means the bigger the slope or the bigger the value of its derivative would be. So when we look at this sine curve, this wave function, just to kind of highlight some things here, um, in this middle chunk here, so from -pi/2 to pi/2, this graph is increasing, which means its slope or the slope of the curve or the slope of the tangent line or its derivative would have a positive value. It changes to decreasing when we get up top here. And at this top point, for a split moment in time at pi/2, it's not changing. It's constant when it reaches that maximum value. But then afterwards, we change over to decreasing. And now the curve is going down, which means its derivative's value or the slope of the tangent line or the slope of the curve would be a negative value. And that change again was made at pi/2. So if we were to find the derivative of this function, its corresponding graph would need to show all those same characteristics. So I'm going to rename this guy f of x because Desmos can show us what the graph of f prime of x looks like. So again, this graph, this red graph, the derivative, is positive from negative pi over 2 to pi over 2, and that corresponds to where the original function was increasing. It is negative from pi over 2 to 3 pi over 2 because that corresponds to where sine was decreasing. And you can see it's going to repeat that cycle over and over and over again because sine is a cyclical function. So if you notice, that red graph is a graph that you guys should know about. That is actually the function cosine. And that is because the derivative of the sine function is equal to cosine of x. So if we start out with the function sine of x, and I want a function that represents the instantaneous rate of change of sine, it is equal to cosine of x. Now cosine, if we were to start off with cosine instead of sine, again, these two functions kind of work hand in hand. Remember, they're actually just shifts of one another. So that's why they behave so similarly. But this guy starts at 0 and is decreasing right off the bat. So from 0 to pi, this is decreasing, which means its derivative would need to be negative from 0 to pi. But then from pi to 2 pi, we're increasing, so its derivative would be positive. So when I graph f prime of x, well, that graph should look very familiar. It's not exactly the sine function that we just worked with, but it looks very similar to it. If you were to compare that to sine of x, it is a mirror image over the x-axis, and that is because the derivative of cosine of x is actually the opposite, or negative, sine of x. So again, there are proofs as to why this is using some the limit definition and trig identities. We can actually see why we end up with this, but again, Newton did that for us already, so we don't really have to worry about it. We can stick with the shortcuts for now. So if I want a function to represent the change of the function y equals 2 sine of x, then dy dx using the constant multiple rule and this first trig rule, we would simply get 2 cosine of x. So again, just very shortcut methods here. Using the constant multiple rule, if I take sine of x divided by 2, again, if the denominator is numeric, then it's really a fractional coefficient. So this is 1/2 sine of x. So then dy dx would be 1/2 cosine of x. That is the function that represents this change. If I have multiple terms, not every function is going to be strictly trigonometric or strictly polynomial. We can mix them. Again, because of that sum and difference rule, we are allowed to mix these any way we want to because we just take the derivative of each individual piece. So the derivative of x would be 1, and the derivative of cosine would be negative sine. So we actually end up with 1 minus sine of x. So this is a fun one. I actually want to take a look at this graph. So it's important for us to establish these relationships between the graph of f of x and the graph of its derivative because it's something that comes up a lot as this course progresses. But if this doesn't make total sense to you right off the bat, that's okay. I don't want anyone freaking out thinking that you're not going to be able to understand anything moving forward. But it's something that we will build upon slowly as the course progresses. So if you look at this graph, this is a funky looking graph. Anytime you mix polynomials and trig, you end up with weird graphs. They do some strange things. You can see it still has a kind of a wave feature to it, but it also has features that y equals x has, where it's um, a function whose limit as x goes to infinity is going to infinity because this guy is going to keep getting bigger and bigger, but we're kind of waving along the way because as we're going, we're going to dip a little bit and then go up, dip a little bit, go up, and so on. But because we're doing it at a slant, it doesn't actually decrease at all. So what's going on here is this graph is actually going to go flat and then increase, go flat and then increase. So as we do this, each time that we go flat for a second, there is a time where we're not increasing. So if we're increasing all but these different individual pieces, where the graph of f increases, remember that means it has positive slope, which means f prime should be positive. But for these moments where we stop increasing for a split second and go flat, that would be where the derivative is 0, because that means that the function is not changing its y value. It's not going up or down. It's staying constant for a split second. So that's why when I click this, you guys see that we are positive everywhere except for these values. So now it's not going to let me click on this exactly, but at pi over 2, that is where this graph goes flat for a second and where its derivative is 0. Over here at 5 pi over 2, that's where it goes flat next, and so on. So each one of those little flat out or flattening spots corresponds to where the derivative equals 0, because again, that is where the graph of f is not increasing for a single value of x. Everywhere else, this function is increasing, which is shown by where the graph of f prime is positive the rest of the way. And if you really want to dive deep into this, if you notice, not only is the function always increasing, but it increases very slowly here, and then it gets steeper and steeper until somewhere right around here we are at the steepest that we ever get. And then we're still increasing, but we kind of taper off the steepness. It goes from really steep here in the middle and starts to flatten out as we approach these really flat spots. Well, if you look at the graph of the derivative, that kind of corresponds to what we see here. We're flat here, so the derivative is 0. We're increasing, but not very steep, so that's why we have positive values for the derivative that are close to 0, but they're still positive, so we're still increasing. But then as the graph of f steepens, the graph of f prime is getting bigger and bigger until it reaches this little local maximum point. So at 3 pi over 2, that is actually where this graph is its steepest value. So it has its steepest slope, its biggest slope, when this f prime is reaching that local max. There's all kinds of really fun, neat, interesting connections that we will make between the graph of f and the graph of f prime. But the more opportunities I have to show that to you guys, I think the better off you'll be as we head forward. All right, another set of rules. So exponential functions. So exponential functions represent a quantity whose growth depends on how much of that quantity is there. So if you remember, exponential patterns mean it's a geometric pattern or a multiplicative pattern. So when I have the function y equals 2 to the x, the way that pattern works is we are multiplying by that base over and over again. So we're going to continue multiplying by 2 over and over and over again to create new y values. So when we start with really small y values, when I double a little bit, it doesn't get much bigger. But if I have a lot of money and I double that, then the increase is going to be much more noticeable. That's why the graph of these exponential functions are very flat when the y values are small. But as we get past that and y-intercept, the y values start to increase faster and faster and faster because we have a bigger y value that we can double. So that's an important concept to understand when we talk about exponential functions. The more or the bigger y values we have, the more noticeable that growth will be. So because of that, that means there's something special going on within these functions when we talk about how they change or their derivatives. So when we look at exponential patterns, we actually see something pretty neat going on. In fact, if I look at a simple sequence, so let's think about powers of 2. So that would be 1, 2 to the 0, 2, 4, 8, 16, 32, 64, and so on. If I do that similar thing that I did earlier when looking at the set of differences for this set that I did for the cubic one earlier in the video, to go from 1 to 2, that's plus 1. 2 to 4 is plus 2. 4 to 8 is plus 4. 8 to 16 is plus 8. Plus 16, plus 32. If you notice, this is the exact same set as before. So this exponential pattern is changing based on an exponential pattern as well. That is a special relationship with exponential functions and their derivatives. There is a direct correlation between the y values of an exponential function and how they grow. So what that means for us for derivatives is we have two special rules here. Now, exponential functions, remember, the base can be any positive value. If it's less than 1 or between 0 and 1, then we have exponential decay. And if it's greater than 1, we have exponential growth. But there are no restrictions. As long as it is a positive value, we can have any base. So because there's so many different bases, how the function changes really depends on what that base is. And so we have it separated two ways because one of the bases is special. So if you remember E is a irrational constant. It's named from Euler. It has a value of 2.71828182846 and so on. It goes on forever. It actually has a special limit that we could dive more into in class if anybody is interested. But it is a special exponential base, and so it has its own derivative rule. It's the easiest one that you guys ever have to worry about. The derivative of e to the x is itself, e to the x. So the way that the y values on e to the x increase are based on exactly what their y values are. So at any given value of x, whatever the y coordinate is, that is also the slope of its tangent line. That is a pretty unique thing as far as derivatives go. So when I look at the function e to the x, let's say that I want to look at the point when x is, 2. So if I want to look at that guy, the value of its slope is actually equal to the value of f of 2. So this y coordinate 7.389 is the same thing as its slope. So it's a pretty interesting relationship. So if you ever come across e to the x, its derivative is very simple. For any other base exponential function, so if it's not e, any non-base e exponential function, its derivative will still be itself, just like e to the x, but because the base is not e, it's going to be a little bit off from the original. So there's a little bit of a discrepancy between the y value of this function and its slope at that point. And that's just because the base is not exactly e, it's something different. So we have to account for that, and we multiply by the natural log of whatever that base of the function is. So that's how this works. So when I come across some of these guys, y equals 3e to the x, okay, well, its derivative would just be, using the constant multiple rule, just 3e to the x again. So again, pray that you see as many exponential functions as possible because they're the easiest to find derivatives of. So that's it for that guy. Next one, f of x equals x squared plus 4 to the x. It is very easy to look at a power term and an exponential term and kind of get them mixed up. So you do have to be very conscious of which rules you're applying. X squared has a number in the exponent, so that is the power rule. So this would turn into 2x. 4 to the x has a variable in the exponent, so that is an exponential function, not a power term. So this would be a non-base e. So I'm going to multiply by natural log of 4 because that's the base, and then multiply by the original function again. So that is the derivative of 4 to the x. And then our last one here, f of x equals sine of x minus 5e to the x. Derivative of sine would be cosine. And then 5e to the x again is itself 5e to the x. These exponential functions are very fun to investigate and mess around with, but as far as coming up with their equations for the derivatives, it's very simple and straightforward. Our last set of rules that we're going to take a look at have to do with logarithmic functions. So the main one that we spend the majority of our time working with in calculus is base e, or remember that's natural log. So remember, every logarithm has to have a base. And that base corresponds to, when we rewrite this expression in exponential form, what base our value of the log function has to be raised to produce a particular power of that base. So base e or base 10, remember those are the two big ones. When we have a log base e of x, we actually write that as natural log of e, or excuse me, natural log of x. If we have log base 10, my pen does not want to work today. Log base 10 of x, we just simply write that as log of x. That's referred to as the common logarithm. Those are the two buttons on your calculator that evaluate logarithms. Those are the two bases the calculator can actually solve for. So when I take the derivative of natural log of x, so natural log of x is the inverse of e to the x. Its graph is fairly interesting. We've talked about it, excuse me, a bit in class already. Remember, e to the x is a horizontal asymptote on y equals 0 and then grows vertically very quickly. Natural log is the inverse of that, so it has a vertical asymptote at x equals 0 and grows horizontally very quickly. So one thing to point out about this guy, though, is this function is always increasing, and it has a domain from 0 to infinity, but it's not including 0 because of that vertical asymptote. So your derivative, remember, a function is only differentiable at points where the original function has a slope. So its derivative also needs to have a domain from 0 to infinity, but not including 0. But if you notice here, this graph gets very steep closer to the asymptote. So it's increasing very, very rapidly near x equals 0. But as we go to infinity, we actually flatten out a lot, and the slope is going to get closer and closer to 0. Well, if I describe that graphically, near the value of x equals 0, where there is a vertical asymptote, this function is supposed to have very large values of slope because the graph is extremely steep. So that would be up here near infinity. And as I go to the right, or as x goes to infinity, the graph is flattening out, or the slope is approaching 0. So that looks like this guy. That is the right half of the function 1 over x. But if I just graph this guy, 1 over x, there are two pieces to it. But again, this piece is unnecessary because there's no part of the natural log function graph over here to match with. So what we often see when we work with this function, there's two ways that this could pop up. Either if I'm just working with natural log of x, it is implied that that derivative has a domain where x is strictly greater than 0. We don't always have to state it because it is an assumed property when dealing with natural log that the derivative's domain matches up with the domain of differentiability for the original function. Another common practice that you'll see happen is rather than starting with just natural log of x, is if I were to start with natural log of absolute value of x, remember we talked about that in class as well, the argument for logarithms must be non-zero and positive. We can't take the natural log or any logarithm of 0 because positive bases cannot produce, the only base of an exponential that can produce 0 is 0. And that's not going to be the case. So the argument can't be 0, and it has to be positive because positive bases can't produce negative powers. So what we do see sometimes is we use these absolute value bars around the argument to allow us to use more x values. So what you're going to see here is if I put absolute value bars around this guy, it makes the left half of the graph. Oh, apparently Desmos can't do that. But if it were able to do that, you guys would have seen, let me see if I can do it this way. Nope, okay, so apparently Desmos does not like that, but take my word on it. If you were able to see this, then you guys would have seen, I'm gonna do it this way. You would have seen that blue part of the graph added on. And what that blue part of the graph is doing as we move left to right is decreasing, and its derivative would match up with the left half of the graph 1 over x. So what you guys see sometimes with these logarithmic expressions, you guys will sometimes see absolute value bars put around the argument. When you come across those, it does not actually change the process of differentiation. All that does is open up the door for more values of x to be used. So when absolute value bars are used, the derivative is simply 1 over x. We don't have to state any extra stipulations or restricted domains because this guy's domain perfectly matches up with this guy's domain. So just want to throw that out there that there are some weird things that can show up with these natural log functions. But as far as derivative rules go, this one's actually fairly simple as well because of the exponential rules so easy, and these guys kind of go in tandem. So natural log of x, its derivative is 1 over x. If I work with any other base besides e, including base 10, then its derivative rule still has that 1 over x part. But again, just like with the exponentials, when we change bases from e to something else, there's always going to be slight differences, and we account for that by, for exponentials, we multiply by natural log of the base. For logarithms, we divide by the natural log of that base. So natural log of a just becomes an extra little factor in that denominator. So for something like f of x equals natural log of 2x, one thing that we want to keep in mind with logarithms is there are logarithmic properties that allow us to expand and condense logarithmic expressions that can actually help us make problems way easier to work with than otherwise. So for example, natural log of 2x, I can actually separate that into natural log of 2 plus natural log of x. And that's helpful to us because natural log of 2 is just a constant. Remember, I'm able to do this because it's a product inside of the argument to start, so I can expand and give each factor of that product its own logarithm with the same base as the original, and then we add them together. So when I go to take the derivative of natural log of 2, this is just a decimal. It's like 0.639 or something like that. So the derivative of any constant, whether it's a nice looking number or some logarithmic expression like natural log of 2, that derivative is going to be 0. So through that expansion, I just get rid of part of the problem. I don't need this part anymore. So this guy is 0. So natural log of x then is just simply 1 over x. So if you really think about that, what that is saying is the natural log of any number times x is going to have this same derivative. So let's explore that a little bit here in Desmos. Let's add a constant in front of here. So when I change this c value, if you look at it very carefully, it doesn't actually look like it's changing the shape of the graph. It actually has the effect of a shift. It looks like it's moving the graph up and down. And what that means is the steepness of the graph isn't changing at all. And that's why we still remain with that derivative of 1 over x. So it's a special little thing that happens because of the expansion properties of these logarithms. Now, for the last one here, f of x equals cosine of x minus log base 4 of x plus 2e to the x. Got everything thrown in here together. So cosine, remember, is negative sine. Helpful thing to remember with trig functions, and we'll see this when we look at the other trig functions coming up in a few sections. Any trig function that starts with a c, its derivative will be negative. So we get negative sine of x. Because this guy is minus to start, then it's going to be minus when we take its derivative. So log base 4 of x, again, it has the 1 over x structure as natural log of x, but we take the natural log of 4 and we write that as a factor in the denominator. It is extremely important that you have parentheses around that quantity. Don't get a decimal value for it. Don't forget the parentheses. Write it exactly as you see it on screen right now. You need those parentheses so that no one mistakes it as natural log of 4x. You don't want that. It's natural log of 4 times the quantity x. And then 2e to the x is simply 2e to the x. I don't know how my tablet thought that was an e. Sorry about that. There we go. So that is it. So again, multiple terms just mean multiple contributions. Take the derivative of each piece as you go. And then for this final example, we got f of x equals 3 natural log of x plus x squared, and we want the equation of a line tangent to that function at x equals 1. So again, I'm writing my point slope form equation, y minus the y coordinate at the point of tangency, times the slope of the tangent line, which is the value of the derivative at the point of tangency, minus or times x minus our c value. So we have our c value is 1. If I plug that in, I get 3 natural log of 1 plus 1 squared is 1. Remember that natural log of 1 is actually equal to 0 because when I evaluate natural log of 1, I'm answering the question e to what power equals 1. That has to be 0. So that term cancels out. So my y coordinate is actually 1. So now I have to take the derivative. So we take the derivative first, and then we'll plug in our point of tangency. So f prime of x, derivative of 3 natural log of x, that would be 3 times 1 over x, or I can simply write that as 3 over x, plus derivative of x squared would be 2x. Now I want to plug my x coordinate of 1 into that. So f prime of 1, my tablet is starting to break down apparently. 3 over 1 is 3, plus 2 times 1 is 2, so 5. So my equation then would be y minus my y coordinate equals my slope times x minus my x coordinate. And that is it.